Welcome back to discussion 32. The last one we did was 29, and then I think 30 is skipped on the sheet, and then it goes to 32, and then there's discussion 31, which will be the last discussion, which I'm not sure why it's in those orders, but either way, I'm just sticking with what's on the sheet. So now we're doing discussion 32. So we're given that a wave is moving along a string. Here's our wave, and it's moving this way along a string. The equation giving the displacement y of a point at coordinate x and at time t has the form this, where the units are in meters and seconds. Great. Calculate the frequency of the wave. This looks very familiar. We've done some stuff like this before. So the frequency of the wave. Well, the frequency is going to be omega over 2 pi, right? That comes from this being over 1 over t, where t is 2 pi over omega. Okay, so what is omega? Well, omega is here as is 20 pi, right? So here we have omega is 20 pi. That's also equal to 2 pi times f. So that means, just so we have it, oh no, that's what we want, actually. So f is equal to, what is it, 10 hertz. Next, calculate the speed of the wave in meters per second. Well, let's recall that the speed of the wave from before, we have omega over k. So this is in 1 over seconds, and this is in 1 over meters, and given that, it will give you units in meters per second. You can also use the relationship lambda f, where lambda is wavelength and this is frequency. We know frequency. And lambda has a relationship with k, right? So k is 2 pi over lambda. And that's equal to 4 pi over 5 from up here, 4 pi over 5. Right, so then that means that lambda is equal to it's 5 over 2. 5 over 2. So then we have, I'm just looking at this, we put this back in here. So V is equal to, let's just make sure that everything works out right. So now we have 20 pi for omega over k, right? And then k, 4 pi over 5. That cancels, that cancels, that cancels, that cancels. This is 5 times 5, so that's going to be 25 meters per second. Also, and then we plug in the other one. So I plugged in this one, I'm going to plug in this one now, just to make sure everything's, to show you that there's 2 ways to do it. Why not? It's fun. Okay, 5 halves times, what was it, 10. So 50 divided by 2 equals 25 meters per second. It's the same. Look at that. So velocity, speed of the wave in meters per second is 25 meters per second. Next, by reflecting this wave from a rigid support, standing transverse waves are set up on a stretched string. It is observed that the string is vibrating in its second harmonic. So n equals 2. All right, well, doing a little organizing. Okay, so n equals 2. Calculate the length of the string in meters. So we have a relationship where our harmonic frequencies are equal to n times the speed of the wave over 2 times L. This is also equal to n times F1. So we know what the frequency is. We found it, right? It's 10 hertz. At the frequency of 10 hertz, we're in our second harmonic. So if we just do this, plug this in, this is where we are right now, 10 hertz. Right, so this is going to be f, where n is 2. And this is going to be 2 times the speed of the wave was 25 meters per second. And then over 2 times the length. So now we just solve for L. Pretty straightforward. These go away. 25 over 10. Right, and this gives you second problem. So we're given that a 50 centimeter long hollow glass cylinder is open at both ends and is suspended in air. A source of sound produces pure frequency placed close to, I'm just reading D32, right? So it's a glass cylinder suspended in air, and then a pure frequency is played through the glass tube, and then we're doing like a frequency sweep. So we're going from low to high, and then we notice that at 320 hertz, the thing resonates. So the resonant frequency is at 320 hertz. Now we want the speed of the sound in the tube. So we want V cylinder. So using the relationship we just used, we can figure this out, where our harmonic frequency is equal to the order number times the speed of the sound in whatever medium it's traveling in, over 2 times the length of the cylinder. In this case, it's half a meter. And then we solve. And so this is first order. So we did a frequency sweep from nothing up to 320, and this is where it first resonated. So now we're using n equals 1, right? So that means this is 1/2, so this is 1 meter, right? 1 meter times 320 hertz is equal to the speed of sound in the cylinder. And that's 320 meters per second. Okay, next part. The frequency of the source is slowly increased, so we're sweeping up again until the resonance occurs again for the third time. Okay, so let's just write down, we had F1 was equal to, what was it? It was 320 hertz, right? And now we're going up again. F3, that we're saying this is the third time, so this is going to be 3 times 320 meters per second over, we'll just say it's 1 meter, right? Because it's 2 times 1/2. So, well, that gives us 960 hertz. Okay, and then the next part, I believe, is we skip the 4th time and we figure out where it occurs for the 5th time. So it's the very similar setup. That gives us 1.6 kilohertz. Okay, so all I did was plug in the number of times that we've run into this, right? And this is where we are. We're on the 5th harmonic, so we plug in 5 for n. Okay, so now the end of the cylinder, one of the ends of the cylinder is sealed, okay? And so now this changes a little bit. It's pretty similar, but it changes, all right? So now we're on part 4. We had 1, then this was 2, this was 3. Now we're on part 4 from the sheet, okay? We do the same thing for a sealed cylinder. So this is what we get for a sealed cylinder. Speed of the sound over, believe it or not, this is going to be 4 times L. So in our case, we have 320. We keep the same speed of sound in the cylinder because we already found that. And then we go 4 times 1/2. Half a meter. That gives you, what is it, 320 over 2. 1 over seconds is equal to half, 1.6. 160. 3, where we plug in 3 times 320 over 2, that actually gives us a value of 480 hertz. So that's the third harmonic. Well, only odd valued harmonics are available in an open, or in a tube where one side is closed and one side is open. Okay, so now we go to the fifth, and then we go 5 halves times 320. That's going to give us a value of 800 hertz. Okay, so still increasing, but a little less, right? So we had 320, 160, right? Then we had 960, 480. Then we had 1.6 and 800. So it's looks like it's about split in half every time. Well, that makes sense. I mean, given that our formula is different by a factor of a half, right? I mean, this is NV over 4L, and our other formula for the open-ended tube was NV over 2L. Provided the speed stays the same, then that makes sense. Next, we're asked, or we're told we place this tube into helium gas, and then asked, do the resonant frequencies referred to in the previous parts increase or decrease? Give your reasoning. Okay, well, so without really doing any math yet, we know that when you breathe in a balloon full of helium, your voice goes higher. So that's an increase in frequency, right? So the frequency goes up when you breathe in helium. Just based on that alone, before I do anything else, I'm going to say that the frequencies are going to increase. But I wouldn't know yet until I look up what is the speed of sound in helium. And that's something that's readily available if you like looking things like this up. And remember, we have this relationship between frequency, speed of the sound, and the wavelength, right? So in a normal, well, I guess what I want to say is in a medium such as air, right? Let's just say we don't leave air, but we want to change the frequency. Well, then that means that something has to change here, right? So if this thing were to, let's say, increase and air stays the same, then this has to decrease, right? So that's the inverse relationship that we have in a stable medium. But now we're talking about changing the medium. And so we want to know what happens to this. Does it go up or down when we place this in helium? Well, if we have a tone happening and then we put it in the medium, I mean, this thing is going to stay the same. That's going to have to be the case. Oops. It's supposed to say same. A-M-E. There we go. It's supposed to say the same, right? So the speed of sound in helium is 1,060 meters per second. So for our resonant frequency, 320 hertz, we had a speed of sound at 340. This is in air, right? Over lambda. This means that lambda is 1.06 meters. Okay, you can try that yourself. So then we plug that in and put 1.06 meters. Well, this means that your frequency is going to be, here, I'll put this down here. So let's say 1060 over 1.06, right? This is speed of sound in helium, and this was the wavelength that we had established in air. We're not changing that. So this gives us 1,000. 1,000 hertz. So we've gone up. Right? In air, we had 320 hertz with the same wavelength. And in helium, with the same wavelength, we have 1,000 hertz. So it's gone up. So that's the reasoning. I would say you have before moving on, I guess we would talk about the reasoning, right? So that would say, I'd say it has to do with the density. Well, helium is, I mean, density of helium is less than the density of air. So I guess there's less stuff to knock into. Okay. Feel free to fill in the gaps there. I know I didn't really go into much detail on that, but all right. So the original air-filled apparatus now suffers a temperature decrease of 40 degrees. Do the resonant frequencies referred to in the previous parts increase or decrease? Okay, so what they're saying is now we have the same tube, and we are decreasing the temperature by 40 degrees Celsius. Well, what do the resonant frequencies do? Again, before doing any math here, I'm just going to guess. I'm going to guess that cold air leads to lower frequencies at the same wavelength. I'm gonna say that. Why? Because slower motion of the molecules results in a slower propagation of the wave through air. That's what I'm going to say. This is my hypothesis of molecules. I'm just going to say moles. I mean slow, slow sound speed. And again, I'm getting this from using this relationship, right? Without changing this, what happens to the frequency that we hear? So if this goes low, then the speed of sound has to go lower too, right? And sure enough, again, this is something you can look up. And what we have, like, this is what I found. So for 1 degrees Celsius, the speed of sound is around 330 meters per second, which is less than the 343 meters per second, which we have, like I say, normal, right? So actually, we had a problem earlier where this was the speed of sound, so it must have been a cold temperature, I would guess. Okay, so this changes. So that's something that is really useful to know. The speed of sound changes depending on temperature and depending on what medium you're in. Okay, so just to wrap this up, 330 meters per second, if we kept the same wavelength from earlier, this gives you a frequency of 311 hertz, and that is in fact lower than what we had earlier. What was it? It was 320 hertz. So due to the temperature difference, it has gone down. Okay, next problem. A violinist tuning her A string is listening for beats with a tuning fork of frequency 440 hertz. She hears a beat frequency of 4 hertz. And what's the frequency of the mistuned A string? Okay. So we have a relationship that we can use as usual, given to us. So we have this 1 over the period of the beat. We could maybe use that. We could use the oscillation speed of the beat over 2 pi. Maybe we could find that. we're told the beat frequency itself is 4 hertz. So this thing is 4 hertz. Right? And then we also have, okay, so this is actually the difference between two frequencies. So let's use that instead. So 4 hertz, because we know one of the initial frequencies was 440 hertz. That's the tuning fork, minus some unknown frequency. Right? And remember, this is the absolute difference in the two, so we could also do this. And okay, so that means that 4 plus 440 hertz is 444 hertz. That was the frequency of the mistuned string. Mistuned string. Right, and so we just found that by considering that a beat frequency is actually the difference between the frequencies that you hear. You can also consider it as 1 over the period, but we were given the beat frequency itself and an initial frequency. Okay, next problem. We're given a figure and it represents a string with length L fixed at both ends, vibrating in several harmonics. For which of these harmonics are the wavelength lambda and length L of the string related by L equals 3 over 2 lambda? Excuse me. 3 over 2 lambda. Well, for a string that is vibrating, that's fixed at both ends, we have this. We have the number of order. We can get this lambda to work. Here we go, and this is over 2. So what does this look like? Well, let's do this. Let's say ln. Okay, so for L1, let's say n is 1, we have this sort of thing happening, right? We have a standing wave that looks like that. It looks like that. Oh, man. You know what I'm trying to do. I think you get it. There we go. Maybe I could just flip this over. I don't know. Oh, I could have just... Okay. Well, anyway, that doesn't matter. So here's your standing wave, right? It's tied here, and it's just one node. Or 2 nodes, it's 1 mode. I guess that's what you would call it. So L2... where, okay, so this is lambda over 2. That's your wavelength by half. Which makes sense, because a wavelength is going to look like this, right? That would be the total wavelength, and we're cutting it in half, and so that's pretty much what we see here. Okay, and now L2 is equal to 2 lambda over 2, right? So it's just lambda. And that would look something like this, like a full wavelength, which is precisely what we just had. So a standing wavelength would look something like that. If you've done lab, you actually get to see these on a string. I'd like this to be, well, anyway, L3, 3 over 2 lambda. What do we have with this? This is going to be 1.5 wavelengths. It's 3 over 2, right? So we're going to go here. Man, I'll get there eventually. There we go. 1.5 wavelengths. Well, it might be a good time, since we've done a few of these, to just check and see on the diagram if any of this matches, right? Do we have these things? So what do we have? We had lambda over 2, that's not what we were given. L2 lambda, that's not what we're given. L3, 3 halves lambda, we are given that, right? And then this matches number 3. C, number 3. So that's it. That's your answer. Okay, D5. A wave is moving along a string, and we have an equation for it. Oh, this is just like a problem that we did 1 or 2 discussions ago. And there's one small difference at the end, so we'll just run through it real quick. I'm not going to spend a lot of time on the first couple of parts because we've actually done all of this. We've done those parts is what I mean. And so 0.15 sine, and we got 10 pi over 60. This is just pi over 6x, right? That's going to be, k is pi over 6 minus 10 pi t. So k is equal to pi over 6. That's also equal to 2 pi over lambda. Omega is equal to 10 pi, which is equal to 2 pi f. So that means that f is 5 hertz. Okay. Lambda then is equal to, well, these go away, right? 12 meters. Now we need to find the velocity of the wave. So I found part 1, right, asks for wavelength. It's 12. I just found it. We've done this before, so hopefully you remember. If not, I went into more detail on this I think 2 lectures ago. Maybe 3 lectures ago. Okay, so this is part 1. Part 2 asks for the speed in meters per second. Okay, remember we had omega over k, or we had lambda f. I mean, we have lambda and f. That's 5 times 12, and this is meters per second. That's 60 meters per second. So that's your answer. Now part 3 is the different thing. By reflecting this wave from a rigid support, standing transverse waves are set up on a stretched string. It is observed that the string is vibrating in its second harmonic. So n equals 2. The frequency of the first harmonic is therefore. Okay, so we've reflected this string, we've reflected the wave back on the string, and we have found that we're in its second harmonic by visually observing the string in the standing wave. So then, if f2, if we're in the second harmonic and we have this frequency of 5 hertz, that means that we are at n times f1, n equals 2, right? So that logically implies that 5 over 2 hertz is equal to 2.5, and that is equal to the fundamental frequency, or the first harmonic, 2.5 hertz. So that's your answer. Right, and I did this, I'm not sure if I was clear about what I was doing, but we have the relationship where we have NV over 2L. We could do that, actually. I don't know. Yeah, that makes sense. And then you could also confirm it by saying we have, well, let's just do this. Just using the formula that we know the speed of the wave. It's not sound, it's just some wave, right? Over 2 times L. Then you could plug in 5. So F2 is equal to 5. Hertz is equal to 2 over 2. Those cancel, times 60 meters per second is your speed. We were told that in L. And then that means that L is equal to 60 over 5 is 12 meters, which makes sense because we were actually told that we're in our second harmonic and our wavelength is, second harmonic would look like this, right? L2, and our wavelength was 12 meters. So second harmonic gives you the full wavelength, 12 meters, and then we're given that we just found that our length is 12 meters. Okay, so that's fine. That makes good sense. So then what about F1? F1 is going to be 1 times 60 over 2 times 12. Well, that's 60 over 24. That's 30 over... We could just divide by 3 right away. You're going to get 20 over 8, right? Over 4, that's 2.5, which is exactly the same as what we got earlier, so that's good. All right, moving on. Oh, that's it. So the answer was 2.5 for that last part. B. Thanks.